Some materials have a tendency to fail when subjected to normal forces, tension or compression, while others in shear, scissors cut by shearing material. Generally speaking, brittle materials have a tendency to break in tension, while ductile materials have a tendency to break in shear. So, to get the most out of the materials we have, we use them in applications where they are strongest. However, it is possible for a material to fail in tension while having only compression and shear applied to it. Moreover, a material can fail in shear when externally it's subjected exclusively to tension. If we do not understand this concept, the structures we design will fail. This video will provide some intuition for the Mohr circle, which expresses the type of stress a material experiences mathematically. A stress is defined as a force exerted over an area, or force divided by area. The element shown on the left is simply a small piece of material I'll define to have 1 unit of area. Therefore, the force equals the stress in this case. Both sigma and tau, the axes on the graph, are stresses. The Poisson ratio defines how an element will deform, shrink, or stretch in the axis not subjected to a force. I only include it to make the animation clear, as you will see the material change shape as forces are applied to it. The Mohr circle will be graphed on the right. The graph x-axis represents the normal stresses, denoted as sigma, and the y-axis represents the shear stresses, denoted as tau. A principal stress is a stress which only has a normal component and no shear component. As a result, the principal stresses always lie on the x-axis of the graph. The red points on the graph will be principal stresses. The Mohr circle is formed by drawing a circle between the points representing the stress applied to each axis. I'm only showing a 2D element, but a real-world element is 3-dimensional, and it is important to consider this axis even when no forces are applied to it. Here, the stress in the y and z-axis is 0, so the circle linking them is not visible. The stress in the x-axis forms 2 circles, one with the y and one with the z. Both of these circles currently overlap. Notice that the maximum shear stress equals the maximum in-plane shear stress. The idea of the Mohr circle is that the element is experiencing a different combination of stresses at different angles. Therefore, the points defining the Mohr circle can rotate together around the circle to determine the stress state of the element at that particular angle. Notice that if we rotate the element by 90 degrees, the x and y stresses would switch. If we look at the Mohr circle, we need to rotate 180 degrees to switch the stresses. Therefore, we expect that a rotation in the element corresponds to a rotation of twice that on the Mohr circle. This will become more clear later. For now, just notice that when subjected to only principal normal forces, rotating 90 degrees in the Mohr circle represents maximum shear. I will apply a small stress in the y-axis. Now we see the importance of considering the z-axis even when there is no stress applied in that axis. The maximum shear stress, the green point, does not change while the in-plane shear stress decreases. If you consider the z-axis as coming out of the screen, we could obtain another 2D element by looking from the top down. This 2D element on the zx plane does not see the stresses in the y-axis, so its state does not change. Now we understand why the maximum shear stress remains constant, but why does the maximum in-plane shear stress decrease? This will be shown shortly. Continuing to increase normal stress in the y-axis, the maximum in-plane shear stress becomes 0 and then increases as the y-axis stress exceeds that of the x-axis. Notice that the in-plane shear stress is 0 when the stress in the x-axis equals that in the y-axis. Once the stress in the y-axis exceeds that in the x-axis, the yz plane experiences the maximum shear stress. This can be seen as the green point transfers from the zx plane to the zy plane. In this case, we can see the Mohr circle if compressive stress is applied in the y-axis instead of tensile. Now the maximum shear stress is always in the xy plane. Based on all of the examples, it appears that the maximum in-plane shear stress is based on the difference between the normal stress applied in the two axes of that plane. With this background, the question, how does shear stress arise when an element is subjected exclusively to normal stresses, can be answered. First, let's consider the characteristic which defines shear. For instance, a deck of cards lying on the table can experience shear if we slide the top card and observe that each card below also shifts slightly. Each card could be thought of as a plane of atoms, so I will draw them as an array of points. Moreover, let's consider what would happen if shear is applied at 45 degrees. Just like with the cards, the further from the center a point is, the more it shifts. Notice how the line passing through the points initially at 45 degrees forms an angle with the original dotted line. This is characteristic of shear. Now, watch what happens when we track the same points as we subject them to a normal stress in the x-axis. Even though we are not directly applying any shear force to the element, the same angle forms. A vertical line would have remained vertical, and a horizontal line would have remained horizontal. However, an inclined line does rotate. Now, why did I draw it at 45 degrees? Because I know that the maximum shear stress, a 90-degree rotation from the principal stresses in the Mohr circle, corresponds to a 45-degree rotation on the element. So this will show it most clearly. But if the line was drawn at 30 degrees, it would still exhibit this rotation, just to a lesser extent. This might inspire the idea that we could end up at the same end state using some combination of shear and normal stresses, applied at an angle to the original stress. This is exactly what Mohr circle represents, the combination of stresses which will result in the same stress state. The order is not important. Let's first apply the two shear stresses, half the magnitude of sigma x at 45 degrees. Next, we apply the normal stresses at half the magnitude and at 45 degrees. We have arrived at the same end state. If we want to know the combination of stresses at a different angle, for example 30 degrees instead of 45, we simply rotate the points in the Mohr circle by twice that angle, or 60 degrees, and read the values off the graph. Now, Mohr circle is looking like a rather useful tool. Recall that the first animation showed in-plane shear stress as 0 when the x and y-axis stresses were equal. The xy plane circle is just a point with shear stress equal to 0, which means that we can arrive at the same end state applying two orthogonal or perpendicular forces at any angle. I will choose 45 degrees for consistency. We see that applying the y-axis force removed the angle induced by the x-axis force. Therefore, we do not expect to see any shear at 45 degrees, which we concluded using Mohr circle moments ago. We simply apply forces equal in magnitude to the original ones at any angle, and the result is the same end state. Loading the element in shear, the points on the Mohr circle move along the y-axis, and the circle extends into the tensile and compressive stress regions. The principal stresses are still 90 degrees from the maximum shear stress on the circle. Notice that the same state could be obtained by applying the green arrows, which are principal stresses, at 45 degrees on the element. With this knowledge, let's consider the example of a material failing in tension when subjected to compression and shear. First, let's apply compression. Great, we're safe. There is no tension experienced by the material. Now, let's add shear. Incredible! The circle is extending into the tensile or positive stress region. Now, we understand why materials can break in tension even when subjected exclusively to compression and shear.